data memory. So as you can see here, all right, so this data memory, the AVR data memory, can be divided into 3 types. Okay, you have 3 types of data memory. Okay, one we call it as a GPR. The second one is IO register, and the third one here is the RAM. Okay, so the GPR is on the top of your data memory. Okay, so this is your GPR, and then you have IO registers, and this is your RAM. Okay, the size of the GPR is you have a total of 32 GPRs, and then 64 is for IO register, and last but not least is your 2 kilobyte for your RAM. Okay, later we will go more details on this memory here. Okay, this register here. So what this register do? Okay, so let's look at the GPR. Okay, the general purpose register. Okay, so AVR microcontroller have many registers for arithmetic and logic operation. So in the CPU, register are used to store information temporarily. Okay, so this GPR here is used to store information temporarily, in which it will be used in order to do data processing such as arithmetics and logic operations. So every time you do the arithmetic and logic operation, you are going to use this GPR. Okay, so the information that you can store inside of this register or general purpose register are a byte of data that you're going to process. Okay, a byte of data means that it's a 8-bit lah. Okay, so the size is 8-bit. 8-bit data to be processed, or an address pointing to data to be fetched. Okay, either you can put a data you're going to process inside of your register, or you can also put the address, okay, of the data that you're going to fetch. So the majority of AVR register is 8-bit register, okay, because in AVR only one data type, which is 8-bit. Okay, so at Mega32, the size of this register here, okay, the size of this general purpose register, okay, is 8-bit. Okay, yesterday we already see that the program memory is 16-bit, but okay, and then we have the data memory 8-bit, while the EEPROM also 8-bit. So with an 8-bit data type, so any data larger than 8-bit must be broken to 8-bit chunks before it processes. Okay, means that if you're going to send out a 16-bit data, so what you're going to do is you need to broken it into 8-bit data by 8-bit data. So you need to have a 2-bit data lah. Okay, so you have a 32-bit data, okay, to be processed. Okay, so what happened here is you need to divide it into 4 8-bit data. Okay, because the register size is 8-bit. Okay, if you have a 32-bit data, so you need to make it smaller. So in AVR, there are a total of 32 general purpose registers. So you have a 32 GPR. Okay, so this GPR, okay, is labeled by R0 to R31. Okay, you have a total of 32 from R0 to R31. Okay, they are located at the lowest location of your memory address. Okay, so recall that this is your data memory. Sorry. Okay, so this is your data memory. If you can see here, this data memory here, you can divide it into 3 types. Okay, one is a GPR, and this is your IO, and this is your RAM. And this GPR here is located at the lowest location of your memory address, which is it started with address 000. Okay, so since you have a total of 32 GPR, okay, kamu ada 32 GPR, so you can find out what is the end address of this GPR, or by using the same formula that we learned yesterday, okay, which is the end address equal to start address plus size minus with 1. Okay, so the start address of GPR is 000. And what are the size of your GPR? You have a 32 GPR. Okay, so we plus with a 32 minus with 1. Okay, then you get 0, 0, 0, 0 plus with 31. Convert this 31 to hexadecimal, then you will get 1F. Okay, so the end address of this GPR is 001F. Right, so the GPR can be divided into two groups, okay, which is a lower register and the upper register. So the lower register is from R0 to R15. Okay, so this is a lower register, while upper register is from R16 to R31. Okay, so this lower register is worth just the rest of the register with the exception of loading immediate data. Means that the lower register, you cannot use any immediate value. Okay, tak boleh guna. You cannot use that. Okay, why? For the upper register, okay, you can use any immediate data or any instruction. So all the instruction can be used in upper register, but for the lower register, the exception is you cannot use any immediate data. Okay, means that, okay, how to know that the instruction have a involve the immediate data or not? Okay, by looking at the instruction, the memory of that instruction. Okay, for example, for the load, okay, to load a data, we have a few instructions to load a data. One is a LD, and another one is LDI. Okay, so this LD here, okay, so LDS, okay. So what the difference between this two instruction here is one involve of immediate value. Okay, the other one not involve the immediate value. Means that, okay, for the LDI, you can only use R16 to R31 only. Okay, cannot use register from R0 to R15, your lower register. Okay, so if you use a lower register, that it invalids. Okay, for example, you put LDI R15 0x75. Okay, you're going to put number 75 to R15. Okay, since this one here involve the immediate value, so this instruction is invalid. Okay, meanwhile, for the LDIs, okay, you can use register from R0 to R31. Okay, so every time you see the instruction that ended with I at the back, so that instruction, okay, involved immediate value. So you just can use R16 to R31 only. Okay, so in addition, okay, the GPR has a pointer register called pointer register X, Y, and Z. Okay, since the pointer register is a 16-bit, okay, so pointer register X is a 16-bit, pointer register Y is 16-bit, and Z also is a 16-bit. So what happened here is you need to, okay, to combine two registers in order to make it as a 16-bit. Because why? Because one register is a 8-bit. So in order to make it a 16-bit, so you need to combine two registers. So the pointer register X is a combination of R27 and R26. So this is an X. Pointer register Y is for combination of R28 and R29. And Z is R30 and R31. Okay, so what this pointer register do? Okay, so this pointer register serve as the pointer for indirect addressing. Okay, so in the next, in the module number 3, you will learn about addressing mode. Okay, so in order to use the indirect addressing mode, you need to know the pointer register. So this pointer register is located at register 26 until register 31. Okay, so to understand the purpose of the general purpose register, two simple instruction LDI and add is used as example. So let's look at the example of the instruction that we're going to look in order to know how the GPR works. Okay, so the first instruction here is LDI. Okay, so this LDI instruction, it copies 8-bit data into your general purpose register. Okay, so this is the syntax. LDI RDK, in which, okay, your RD is your destination register, while the capital K here, okay, this big K here, is the value that you're going to load. Okay, it is an immediate value. Okay, so this RD must from R16 to R31. Why? Why you need to use the R16 to R31? Kenapa? Anyone?
Because this instruction used for load immediate value.
Yes, you're going to load the immediate value. Okay, you see here, at the end of this instruction here, you see the I. Okay, so means that it involve the immediate value. So that's why we need to use the R16 to R31 only. Okay, so this K, okay, since this is an immediate value and the value is an 8-bit value, so this value can be from 0 to 55 in decimal or 0 to FF in hexadecimal. Okay, so this is your 8-bit data. If you put 00000 means that this is a 0 in decimal or 00 in hexadecimal. If you put 11111111, so this is FF in hexadecimal or equivalent to 255 in decimal number. Okay, so this is 8-bit data. Okay, so let's look at the example here. Okay, you're going to load R20 register with a value of 25. Okay, now you're going to load. Okay, sorry. Okay, so this is your R20, is somewhere around here. Okay, because the top here is your GPR and this is your IO and this is your RAM. Okay, so this is your data memory. So R20. So now what you're going to do is you're going to load this value 25, which is an immediate value from outside to your R20. So how to do that? Okay, since this is an immediate value, which is a value from the outside, okay, you're going to put it to R20. So you can use the instruction LDI R20 followed by 0x25. So what happens after you execute this instruction here? Okay, after you execute this instruction, number 25 will be stored inside of your R20. Okay, so this is what the LDI instruction do. Okay, to copy a 8-bit data or to load a 8-bit data to your general purpose register. Okay, next we look at the ADD instruction. Okay, so this ADD instruction used to add the value of RR to RD and put the result back in your RD register. So this is the syntax. Okay, so you see here ADD RD, which is your destination register. RR is your source register. And after you do the addition, okay, what happened here is you put back the result to your RD. So RD equal to RD plus RR. Okay, so RD and RR is your general purpose register lah. Okay, it can be from R0 to R31. Okay, for example, okay, you're going to add two numbers, which is, okay, you're going to add 25 plus 34. How to do that? Okay, first, can we use the ADD 0x25 0x34? Can we use this? Can or cannot? To do the addition 25 plus 34.
You can.
Oh, cannot. Okay, we cannot. We can't do that. Why? Because if you see the syntax here, okay, it involves the GPR with a GPR, not a constant number. Okay, so this one is a constant number or immediate value. Okay, so this one is invalid lah. So what you're going to do? Okay, since this one here, this number is immediate value. So what you're going to do is you need to load this number here to your register. Okay, load this number to your register. Let's this one you put to R20, and this one you put to R22, for example. And after that, you can use the ADD instruction. Okay, so the solution is, okay, in order to add these two numbers here, first, you need to load value 25 to R20 by using the LDI instruction. So LDI R20 0x25, and then so what happened here is, so R20 now will have value 25, and LDI R22 0x34. So after you execute this line here, R22 will have number 34, and after that you can use the ADD instruction. So ADD R22 R20. Okay, you can put R20 R22 also can. Okay, so what happened here is R22 equal to 34 plus with 25. Okay, so the result here is 59 after you add these two numbers here. Okay, 59 will be stored to your R22. Okay, any question? This is how we're going to use the register in order to do arithmetic operation or logical function.
Sorry, Doctor. What do you mean by the immediate value? Like
Okay,
how you identified.
Okay, immediate value means that the value that not inside of your data memory. Okay, the outside value. Okay, if the value is inside your data memory, so that one not belong to immediate value lah.
Okay.
Okay, so another example. Let's say. Okay, so let's say. Sorry, not that one. Okay, so this is your data memory. Okay, let's say this is your R19 and R20. So R90 already have 25 and R20 already have 34. So you're going to add this number here, 25, 34. Do you need to do these two instructions here?
No.
No. Why? Because the value is already inside your GPR. So no need to do these two instructions. Okay, no need to load the 25 to your GPR. Okay, so what you're going to do is you just use the ADD R19 R20 because the value is inside the GPR, already inside the GPR. Unless the value is outside, which is not stored inside your data memory, then you need to load that value to your register.
Okay.
Okay, so that is for the general purpose register. Okay, so this one here. Okay, now we're going to look at this IO register. Okay, at the middle of this data memory. So the IO register is dedicated to a specific function such as a register, status register, timers, serial communication, IO ports, ADC, and etc. Okay, so previously we already learned about the I/O ports. Okay, in which each of the I/O port will have a 3 main register, which is a DDR X register, port X register, and pin X register. So all of this register actually is located inside of I/O registers. So the function of each I/O register location is fixed by the CPU designer. So you cannot reprogram, or you cannot change the location, because it's been fixed by the CPU designer. So the number of location in the data memory set aside for I/O register depend on the pins number and the peripheral functions supported by that chip. Okay, so all of the AVR have at least 64 byte of I/O register location called standard I/O register. So now, okay, so for Amiga 32, we have a total of 64 I/O register. Okay, so previously, okay, we already done the calculation, okay, for the address of GPR, which is the starting address is 0000000, and the end address of GPR is 001F. Okay, now we're going to find out what is the end address of our I/O register. Okay, so what is the starting address of I/O register? Can you tell me what is the starting address of I/O register? Okay, we're going to need to use this formula. Okay, the end address equal to start address plus size minus 1. Okay, so what is the start address of I/O register? Anyone?
20?
Okay, 20, correct. So 0020. This is the starting address of your I/O register. So 0020 plus the size of I/O register, which is a 64,
64.
minus with 1. Okay, so you will get 0020 plus with 63. Okay, convert this to hexadecimal and you add with 20. So what you will get? What is the value?
I think 85.
Huh? 55. 63. Okay, convert this one here to hexa number and then add with the 20. 5F. Okay, so the end address of the I/O is 005F. Okay, can you see here? Okay, so this is the I/O register. Okay, I will zoom in. Okay, so this is the I/O register. Okay, we have a total of 64 I/O. Okay, so the register that you will going to look at is, okay, this register, ADCL, ADCH, ADCR, ATMA, and sorry, not this one. Okay, so ADCL. Okay, so this one here, this is belong to ADC, analog to digital converter. So this one we will learn in the module 13, if not mistaken. Okay, and then okay, so this one here, this is your the one that you always use. Okay, pin D, DDRD, port D, pin C, DDRC, port C until here. All right, so this is for your I/O input outputs register. Okay, then we have, okay, this one here, this registers here, OCR2 until, okay, until this here. Okay, so this is belong to timer register. Okay, so you will learn how to do a timer, how to create a delay. So this is the register that you're going to know. And last but not least is this one here. All right, so this is for interrupt register. Okay, this one, the interrupt register as well. And these two here, SPL and SPH, is for the stack pointer. Okay, so this one you will learn in module 8 if not mistaken. And last but not least is SREG. Okay, which is this is the status register. Okay, so this is the register that you need to know. Okay, ADC registers, IO registers, timer registers, interrupt registers, stack pointer as status registers. So now in the next few slides, we will learn about how to obtain the data, how to move a data from IO register to GPR, from IO register to our RAM. Okay, so that one is for the IO register. And then next we go to SRAM, okay, which is, okay, if you, I draw again. Okay, so you have a GPR here, and then you have IO here, and this is your RAM. Okay, so the end address of the IOs just now is 005F. Okay, now you know that the static address of your RAM is 0060. Okay, so internal SRAM or RAM widely used to store data and parameter by AVR programmer and compiler. So this is another memory in order to store data temporarily. Okay, if your GPI is full, then you can store the data inside of your RAM. So each location of the RAM can be accessed directly by its address. Okay, you can access the data inside of this RAM by looking at the addresses. Okay, the RAM address. So each location is 8-bit wide and can be used to store any data you want. Okay, so again, okay, the size of your data memory, which is your GPR, IO register, and RAM, are 8-bit wide. Okay, so since the RAM is the size of RAM is 2 kilobyte, so now we're going to find out what is the RAM end. Okay, the end address of your RAM. Okay, by using the same formula, okay, the starting address is 0060 plus with size, which is a 2 kilobyte, minus with 1. So you get 0060 plus with 2. Okay, 2 kilobyte, convert it to bytes. So you get 1024 minus with 1. So 60 plus with 248 minus 1 is 2047. Okay, convert this value here to hexadecimal. Then what is your RAM end after you add with 60? Berapa dapat?
85F.
Okay, 085F. Okay, so you need to remember, okay, the RAM end, okay, your end address of your RAM is 085F. Okay, this is only for the Atmega 32 lah. If you use another chip, the RAM end will vary according to the size of that RAM. Okay, so just a quick recap. Okay, so AVR architecture, we have 3 separate memories. Okay, we have a flash program, we have a data memory. For the data memory, we can divide it into three parts, which is you have a 32 general purpose register, 64 input-output register, and 2 kilobyte of internal RAM. Okay, and then followed by the EEPROM. Okay, so this is the size and the end address for each of the memories. Okay, now we are going to see the instruction. What are the instructions that we need to use in order to access or to do a data movement inside of the data memory? So earlier we already see the Ldi instruction and ADD instruction that use immediate data or constant value of K in GPR. So now we are going to see another instruction that allowed us to direct access to other location in the data memory, such as your RAM and the input-output register. Okay, instead of you can access the data inside of your GPR, you can access the data inside the input-output as well as your RAM. Okay, so now let's look at the third instruction for today, okay, which is the LDS instruction. So this LDS stands for load direct from data space. Okay, it tells the CPU to load or copy 1 byte of a data from an address in the data memory to GPR. Okay, means that, okay, for this one here, what happens if you use the LDS? Okay, so you take the data from your RAM, okay, and then copy it to your GPR. Okay, so this is what the LDS do. Compared to LDI, so what the LDI do is you take a data, okay, you take a value, immediate value from outside and put it to your GPR. Okay, that is the difference between LDS and LDI. So after the instruction is executed, what happens here is the GPR will have the same value as the location in the data memory. Okay, for example, okay, you're going to load R5, okay, with a content from address 200. Okay, so this is your address 200 inside of your RAM. Okay, you're going to take the value inside of this RAM and put it to your R5. So how to do that? So you can use the LDS instruction. Okay, so what is the syntax of the LDS instruction? Okay, this is the syntax of LDS instruction. Okay, LDS, RD, and this is a K. Okay, this one, the K here is a small k actually, not the capital K. Okay, the capital K indicate that one is belong to immediate value, while the small k indicate that one belong to memory addresses. Okay, so let's look at the instruction set. Okay, so this is your instruction set summary. Okay, I will give to you after this. Okay, so let's look at the LD. Okay, here, this is your LD. Okay, I zoom in. Okay, so this is your LD, and this is the LDS. Okay, you see here, LDI is RD with capital K, while LDS is RD with a smaller k. Okay, so what happened here? The capital K means that this is an immediate value. You're going to put it to your RD, while the smaller k here is the value from the memory address. You're going to put it to your RD. Okay, for the load, okay, we have a few other instructions for the load. We have a LDI, LDAs, then you have a LD, LDD, and etc. Okay, later we will see more about this instruction, okay, in the next module. So now, in this example here, you're going to copy whatever value inside of address 200 to your R5. So how to do that? You just simply write, okay, simply use the LDS instruction. So LDS R5, which is our destination register, and K is your source address, okay, which is at address 0x200. So what happens after you execute this line here? So the value from address 200, okay, tak kisahlah, either it is inside of your RAM or it is inside of your IO register, will be copied to your R5. So after you execute, okay, so R5 will have the same value as address 200. What happened to the content inside the 200? Okay, the content is remain, no change after you execute this instruction. Okay, another example. okay, you're going to add the contents from location 300, okay, and 302, and put it back to the 300. Okay. Okay, you're going to add two value that is stored at address 300 and 302. So how to do that? So you know that, okay, 300, okay, and 302. Okay, somewhere around here lah. So how are you going to do? Okay, firstly first, ADD. Okay, so ADD saying that ADD must be between register with register. Okay, you cannot add from RAM or from immediate value. Okay, so since this value here is already stored inside of the address 300 and 302, so what you're going to do is you need to load this value to your GPR. Okay, and then once you already load this value to GPR, then after that you can add them. Okay, so this is step number 3. Okay, so what you're going to do is by using the LDS. So LDS, okay, for the LDS, we can use from R0 to R31. Okay, there is no restriction. Okay, you can use any registers, any GPR. Okay, so you can use the R0, R1. Okay, for this example, I just use the R3 with a value from address 300, and then load again LDS R4 with a content from address 302, and after that, sorry, I add them ADD R3 with R4. Okay, so this is the explanation. Okay, this is the graphical explanation in which, okay, first what you're going to do is, okay, you go to address 300. Okay, take whatever value inside here and put it to your R0. Okay, in this case here, it use the R0 and R1, so it will store to R0, and then load again whatever value inside of address 302, put it to R1, and after that you add them together. So any question up until here? Ada soalan tak? Okay, if no question, so now we go to the another instruction, which is called Sts instruction. Okay, so this instruction here, store direct to data space, means that you're going to store the value from GPR to your RAM, okay, to an address location. Either it is in your RAM or it is in your IO register. Okay, as long as you use the address location, then it will be stored there. Okay, so the syntax for this instruction is STS KRR, in which K is your address between 000 to FFF. Okay, actually for Atmega 32, okay, after we did the calculation earlier, okay, what is the end address of our Atmega 32? 085F. Okay, so the address here can be from 000 until 085F. Okay, not FFFF. Okay, and then KRR is your source register. Okay, the source register can be from R0 to R31. Why? Because we not invoke the immediate value. So after the instruction is executed, the location in the data space will have the same value as a GPR. Okay, for example, you're going to store the content of R35 to location 230. So what you're going to do is here is, okay, let's say lah, okay, so this is R25. Okay, you have a content inside here. Let's say I put it 2F, for example. Okay, the value inside R25 is 2F. Okay, now this value here, you're going to store it in address 230. Okay, so how to do that? Okay, we can use the Sts instruction. Okay, in which Sts, okay, what is the destination that you're going to store? Address 0x230 from what source? Okay, what is the register source? R25. Okay, so after you execute this line here, what happens is the 2F, okay, this value here will be stored inside this address. Okay, and the value 2F will remain in the R25. Okay, no change. Okay, so next, load the R16. Okay, another example here. Load the R16 register with a value of 55. Okay, you're going to put 55 to R16. Okay, then move this value to your port B, port C, and port D. Okay, so okay, you already know that the port B, port C, and port D is actually a register that is inside of your I/O register. So what you're going to do is, okay, you need to know the location. Okay, what are the memory address of this port B, port C, and port D register? How to get the address? By looking at this table here. Okay, so by looking at this table, you can see here there are two address. Okay, there are two address. One we call it as an I/O address. The second one here we call it as a memory address. Okay, so for the STS LDS, okay, we will focus on the memory addresses. Okay, if you use the in or out instruction, then after that we use the IO addresses. Okay, you see here you have two columns. One is for the input output address. The other one is a memory address. Okay, so in this example, we are looking at the STS, which is you need to refer to memory address. Okay, so now we're going to find out what are the address for port B, port C, and port D. Okay, so port B, this is your port B. Okay, the address here is 38. Port C, where is your port C? So this is your port C. Address is 35. And port D address is 32. Okay, the memory address is 32. Okay, so now you're going to write the program. Okay, you already know the addresses, so you're going to write down the program. Okay, so first, what you're going to do is, okay, so I just write down here. So this is your port B, and this is your port C, and port D somewhere around here lah. Okay, so tadi this one is at 32, 35, and this is at 38. Okay, so you're going to send this value 55 to your port B, port C, and port D. So how to do that? Since the value 55 is not stored inside of your GPR, so what you're going to do is you need to put this value to your GPR first. Okay, so that's why load I R16 with 0x55. So what happened? R16 now will have value 55. And after that, okay, since the R15 already have 55, then after that, you can copy or store this value to your port B, C, and D. So by using the STS, okay, we're going to store to port B. What is the port B addresses? 08, 0x3, 8. Okay, so this is your port B. Okay, so what value that you're going to store? Okay, 55 from which register? Okay, because this is a register source register, so from R16. Okay, then store again STS08. Okay, now you're going to store to the port C. The port C address is 35 with R16 and STS0X32 R16. Okay, so this is how you're going to move the data. Okay, move the value 55 to your port B, port C, and port D. Any question up until here? Okay, if no question, then we move to in instruction. All right, so this in instruction, okay, stand for in from IO location. Okay, tell the CPU to load 1 byte from IO register to GPR. Okay, so this one here, it only focus on IO to GPR or IO GPR to IO. Okay, so let's say if you're going to copy a data, okay, from IO to your GPR, okay, you can use the in instruction. Okay, if you're going to store the value from GPR to your IO, you can use the out instruction. Okay, so let's look at this in instruction. So this in, okay, this is the syntax here. In RDA, okay, RD is your destination register, can be from 0 to 31, while A is your IO addresses. Okay, so the IO address is from 0 to 63. Why 0 to 63? Because you have a total of 64 IO registers. So that's why it's 0 to 63. But this 63 is actually in decimal number. Okay, by right is from 0 to. Okay, so now since this is a IO addresses, so we need to refer to this column lah. Okay, the left column here. Okay, the IO addresses. Okay, where are we? Okay, so each location in IO memory address has 2 address. Okay, as I mentioned earlier, for IO register, it have 2 address. One is a data memory addresses, and the other one is IO addresses. So address of each IO register in comparison of the. Okay, so this IO address, okay, referring to the, okay, is used for the in and out instruction, while the data memory address is used for the LDS and SKES instruction. So in instruction, the IO register are referred to IO address. Okay, by using the in instruction, now we need to refer to IO address. Okay, cannot refer to data memory address. Okay, because the data memory address only for LDS and SKES instruction. Okay, for example, okay, you're going to load R19 with the content of location OX10 of the IO memory. So how to do that? Okay, you just simply write down in, okay, R19. Okay, this is your destination register. And then from what address? 0x10. Okay, so you take any value from this address. 0x10 is actually around here because this one we refer to IO address. Okay, so it's actually around IO register, okay, inside of this region, and you put it to R19, which is equivalent if you use the LDS. Okay, LDS R19. Okay, now we need to find out what is the data memory address for this location. Okay, so we refer back. Okay, so this is the same table. Okay, so address 010. So 010, where is a 0? Okay, now the column is switches. Okay, you see here. Okay, at the right hand side now it become IO, and the left hand side here is your memory address. Okay, so now we're going to see the 10. Where is our 10? Okay, this one here. Okay, actually refer to pin D. Okay, so 10 is actually a pin D registers. Okay, so the memory address of the pin D is actually 30. So it equivalent to OX30. Okay, you can either use this instruction or this instruction number 2. Okay, both do the same thing. Okay. Okay, so to work with the IO register more easily, okay, we can use their names, okay, instead of the IO addresses. Means that, okay, you no need to remember the IO addresses. Okay, we just, okay, in order to access the IO register, we just refer to its names. Okay, so this is the name you need to refer. Okay, so no need to remember all these addresses. Okay, you just need to know the name of your IO register. For example, load R19 with the content of pin D. Okay, which is we already did here. Okay, just now we use the IO address by using the instruction, and we use the memory address by using the LDS, which is this one also. Okay, you have another instruction which is do the same thing by using the register name, which is R in R19. Okay, with pin D. Okay, so all these 3 instructions do the same things. Okay, you're going to take the value from the pin D register and put it to your R19. Okay, my advice is, okay, you better use the in and out instruction whenever you're going to do a data movement between your input output register and GPR. Okay, why? Because we can use the name instead of need to remember the addresses.
Doctor, I have
Yeah.
question. I have question.
Yeah.
If destination register use BND is valid or not valid?
You use
Destination register BND, it's
pin
valid
D.
or not? BNB, yes. Is valid or not valid?
Pin B.
Use it as we use it as destination register.
Destination register. If you use the destination register, not valid. Why not valid? Okay, we need to refer back to our syntax. You see the syntax here?
Yes.
The destination register is only from GPR, General Purpose Register.
Yeah.
Okay, so that one is not valid.
Thank you.
Okay. Okay, so this is for in instruction. Now we go to the out instruction. Okay, so out stand for out to IO location. Tells the CPU to store GPR, okay, any content inside of your GPR to your IO register. And this is the syntax out ARR. Okay, so RR is your source register. A is the IO address. Okay, so this source register must from your GPR, okay, from R0 to R31. Okay, from R0 to R31. Okay, and then the A here, the A refer to your IO addresses. So after the instruction is executed, the IO register will have the same value as GPR. Okay, so for example here, okay, you're going to copy this value E6 to SPL. Okay, so you're going to copy E6 to SPL. So SPL is somewhere around here lah. So how to do that? First thing first, okay, you need to identify, is this E6, this value inside of your data memory? If no, what are you going to do? Okay, if no, you're going to load it to your GPR by using the Ldi instruction. Okay, so after you load to the GPR, then after that, you can send it to your SPL by using the out instruction. Or you can send it by using the Sts instruction as well. Okay, but for this is example, we use the out instruction. So what happened here is, so you use the LDI. Okay, so you're going to put this value to what register? Okay, let's say I put the R30. Okay, with 0x E6. So E6, okay, will be stored to R30. Okay, then after that, by using the out instruction, out, okay, where are you going to put that value to SPL R30. Okay, so that is the out instruction. Okay, another example. Okay, let's look at another example down here. Okay, you're going to copy a value from pin D to port A. Okay, now, okay, so let's say like this is your pin D, and this is your port A, guys. Okay, so pin D, and this is your port A. Okay, let's say inside of this pin D have a value 7, 5, for example. Okay, now you're going to copy this value and put it to port A. How to do that? Okay, can you directly use the out port A pin D, because this is your destination and this is your source. Can you do that? Cannot. Anyone?
We can't.
Okay, can't. Okay, you cannot do that. Why? Because from the syntax here, okay, you see the source must from your GPR. Okay, so what you're going to do is here is, okay, you need to copy this value to your GPR, and then after that, you send it to your port A. Okay, so this one you can use the in instruction, and this one you can use the out instruction. Okay, so that's why. So this cannot, so not valid. In R29, for example, okay, pin D. So what happened here is R29 will have the same value of pin D, which is 75. And after that, our port A R29. So port A now will have the same value from 29. Okay, so this is the out instruction. And then we have a MOV instruction. Okay, so MOV used to copy a data among the GPR register. Okay, so this MOV, what this MOV do means that you're going to copy a value or content from one register to another register. So this only valid for between GPR. Okay, so this is the syntax MOVRDRR. And for example, okay, you're going to copy the content of R20 to R10. Okay, so this is R20 and this is R10. Okay, so how to do that? Okay, by simply write MOV. Okay, what is your destination register? R0. Source register R20. So what happened here is R10 will have whatever value from 20. Okay, so this for the Mov instruction. Okay, actually we have a lot of instruction actually. Okay, we have 100 instruction. So in the next few weeks, you will learn about all of these instructions. So what this instruction do? Okay, no need to what we call it. Okay, you no need to worry. Okay, because this instruction set will be given inside of in your final exam and in the test. Okay, so no need to remember. As long as you can know what this instruction do, so that's it. Okay, because from this instruction set, okay, it already tells you what are the mnemonics, what are the operands, description, and operation for each of these instruction. Okay, by looking at this operation here, you know lah what the instruction do. And this is the flex affected every time you do the what we call it, every time you execute the instruction, and this is the clock cycle that I told you in the last week. Okay. Okay, so let's look at the more ALU instruction involving the GPRs. Okay, so we have the INC instruction. Okay, so this INC instruction used to increment the content of RD register by 1. So this is the syntax INC RD, which is you going to increment the content of RD by 1. So what happened here after you execute this line? So RD equal to RD plus 1. Okay, for example, you're going to add 1 to the content of R2. So just use the increment R2. Okay, so R2 equal to R2 plus 1. Okay, you have two solutions here actually. Okay, one is the longer way, the other is the shortest way. Okay, so the shortest way here is you just use the INC R2. Okay, whatever the value from R2, so we will be incremented by 1. Okay, so the longer way, okay, the second solution, okay, first, let's say lah, the initial value of R2, okay, sorry, let's say you don't know the initial value of R2. So since you're going to add with 1, okay, for the second solution here, you're going to use the ADD instruction. So what you're going to do here is now you need to load this value 1 to your register because the ADD instruction is between two registers. Okay, so load this value to your register. Let's say this one you're going to load to R17, for example. So LDI R17 with 1. Okay, and then ADD R2 with R17. Okay, you see here, this is only one line instruction needed, but this one you need to have 2 lines of instruction. Okay, another example. Okay, increase the content of data memory location at address 430 by 1. Okay, you have this data memory. Okay, so 430 is somewhere around your RAM. Now you're going to increase this value by 1. So how to do that? Can we directly use the INC 430? Boleh tak?
No.
Okay, cannot. Okay, because you see here the syntax here is registers. Okay, must use GPR. So what are you going to do? Okay, first you need to load this value to your GPR. After that, you increment by 1. Okay, so this is a second. Okay, you increment by 1, and then the next instruction. Okay, the next one, the next step is you store it back to this location 430. Okay, by using the Sts instruction. Okay, so this one you can use the Lds instruction. Okay, so that's why you see here LDS R20 with the from the location of 430, increment that R20, and after that use the STS to store the increment value to address 430. Okay, next we have a DEC. Okay, so D is for the decrements. Okay, the content of RD by 1. So this is the syntax DEC RD. Let's look at the example. Subtract 1 to the content of R10. Okay, so you can simply use the DEC R10. Okay, again lah. Okay, this one here. Okay, you can use the longer way or the shortest way in order to do this example here. Okay, the shortest way is by using the DECR R10, while the longest way here you need to load 1, okay, to your registers, and then by using the SUB instruction, then sorry, not R17, this is R10. Okay, then after that, you decrement it by 1. So this needs 2 lines of instruction, and this only needs 1 line of instruction. Okay. Another example, put the value 3 into R13, then the value of R30 is decremented 3 times. So how to do that? Okay, so since the value 3 is an outside value, which is a constant or immediate value, so you need to load this value here to your R30 by using the Ldi instruction, and after that, by using the decrement DEC instruction, you decrement it 3 times. Okay, so decrement R30, and decrement R30. Okay, next is SUB. Okay, so this SUB instruction tells the CPU to subtract the value from RR from RD and put the result back to the RD register. So this is the syntax SUB RD RR, in which RD and R can be from R0 to R31. Okay, so what happened here is, okay, so you need to look at this operation here. RD equal to RD minus RR. Okay, for example, you're going to subtract 25 from 34. Okay, you have a 34 values going to minus with 25. How to do that? Okay, again, since this is a constant number or immediate value, you need to load it to your register. Okay, so just put it to R20, and this one is to R21. And after that, then you can do the subtraction. Okay, so LDI R20 34, LDI R20 25, and then SUB R20 R21. Okay, don't swap the position. Okay, do not write SUB R21 R20. Okay, if you write this, then the answer is wrong. Okay, means that this one here, instead of you going to do this operation 34 minus 25, so what happens when you do this thing, when you execute this line here, now what happens is 25 minus with 34, so you will get the different answers. Okay, the wrong answers. Okay, so make sure that the location of destination and race, okay, source is correct lah. Okay, another example, subtract 5 from the content of location 300 and store the result to location 320. Okay, so please change this one to 320. Okay, why? Because our RAM end, okay, only up to 085F. Okay, you need to remember this one. Okay, for Omega 32, okay, the RAM address, the last address of our RAM is 085F, unless, okay, unless you you install another external RAM, then okay, it can reach beyond that, beyond this value. Okay, so how to do that? Okay, you have a value from address 300. Okay, you're going to subtract with 5, and then after that, the result will be stored to address 320. So macam mana nak buat? How to do that? Anyone? Yes, so it is 300.
I think, Doctor, we use XY register,
X5.
XYZ registers.
Well, for this one, no need to use the SYZ register, the pointer register. Because
it has
because
16-bit.
okay, actually, this is not this is not the data inside of this is only the memory address, not the data.
Okay.
Okay, so this is your memory address. Okay, outside here, this is your memory address, and this is your data. Of course, like the size of the data must be 8-bit, but the memory address can be more than that. Doesn't matter. So in this example, we no need to use the pointer register X, Y, and Z. Okay, so you have the value. So let's say like this is the value here. X, I put 9 lah, 09. Okay, so the value inside of the 300 is 09. Okay, so the value is 09. You're going to minus with 5. So by right at 30, address 320 will store value 4. Okay, 0, 4. Okay, you're going to store the 04 inside of your 320. So how to do that? Okay, first 5. Okay, so first, okay, this 5 here actually a constant number or immediate value. So you need to put it to your GPR. Okay, so this is the first step. Okay, the second step, okay, you're going to take this value from address 300 and put it to your GPR as well. Okay, so this is the second step. After that, you do the subtraction, and the result of that subtraction you will store to the address 320. Okay, so this is the fourth step. Okay, the first step here you can use the Ldi instruction. Second step, what instruction that you're going to use? To load the value, okay, or to load the content of address 300 to GPR, what instruction?
LDS.
Okay, LDS. And then number 3, you can use the SUB. What about number 4? To store the result to address 320.
STS.
Okay, you can use the STS. Okay, so LDI. Okay, you can choose any register from R0 to R31. So in this case, we just use the R17. Okay, and then load with number 5. Okay, just to mention, I think I already mentioned previously before. Okay, if there is no symbol in front of these numbers here, so this number will represent a decimal number. Okay, if there is a symbol of 0x or sometime, okay, you will see the $ symbol. So that one belong to hexadecimal number. Okay, if you see the 0B, okay, that one is belong to binary numbers. Okay, since this one here, no symbol in front of this number, so this is a belong to decimal number. Okay, and then we have LDS, okay, R18, for example, from what address? 300, so OX 300. Okay, and then after that, step number 3, you're going to subtract, okay, address from 300, okay, the content from 300 minus with 5, so SUB R18. with R17, and the result will be stored to R18. Okay, so what happened here is, okay, R18 sama dengan 09 minus with 05, which is the value will be 04. And after that, you're going to store this result here 04 to this memory address 3220 by using the STS. Okay, so STS 320 value from R18. Okay, so this is the instruction to do this, to solve these examples. Okay, so any other instruction, ALU instructions such as, okay, we have a plenty of instruction actually. Okay, some of them such ADD, we already see that. ADC, so ADC is actually add RD and RR with carry. Okay, this one here we will see more details on module 4, if not mistaken. And then we have the logical function. Okay, so this is the logical function and exclusive or, and then we have the SBC and sub. Okay, so this is the subtract. SBC stand for subtract RR from RD with carry. These are the instructions for that involve the GPR. Okay, so this is your GPR. Okay. And then, okay, so this is some of the example of instruction using a GPR. Only involve one GPR. Previously, we see the involve two GPRs. Okay, this one here using the two GPRs, but this instruction now use one GPR. Okay, so the example here such as the CLR. Okay, means that every time you put the CLR, what happens here is you're going to clear the register. Okay, for example, okay, you're going to clear R20. Okay, you're going to make your R20 so that your R20 value will be 0. So how to do that? Okay, just simply use the CLR R20. Or, okay, you can use the LDI R20 with 0. Okay, so this one both do the same thing. Okay, which is you're going to clear the R20. Okay, this one is increment, okay, decrement, and then you have the com. Okay, so com is the first complement. Okay, if you're going to do the first complement, then you can use the COM instruction. And then NEG is a negative, which is this is for the two complement. Every time you're going to do a two complement, you can use the NEG instruction. And then this is a ROL, ROR. Okay, so this is a rotate instructions. Okay, you will learn in the module 7. Okay, and then we have the swap. Okay, the swap is actually to swap a nibble in RD. Means that, for example, okay, R17, you have value 17. Okay, if you put as swap R17, so what happened to R17? Okay, the location here, okay, the value of low neighbor and high neighbor will swap position. Okay, so this one will go to here and this one will go to here. So what happened here? After you execute this line, R17 will have 7, 1. Okay, so this is what the swap do lah. Okay, so this one you will learn more details in the next module. Okay, now I got to focus.
Doctor?
Yeah.
So any values stored in the registers, as soon as they're negative, they're stored in 2's complement?
Can you repeat once more?
Like any negative value stored in the registers, it's stored in 2's complement?
Yes, the negative value will be stored in the two complements. Okay, if you're going to what we call here, to do a negative to process a negative number, you need to convert it to second complement, two complements. Okay, for example, if you're going to store the R5 with -5, so you need to find out what is the value of two complement for -5, and then after that you can put the value to your R5.
Okay, doctor, thank you.
Okay, welcome. Okay, so the way how to do a second complement, I will show you in the next module. Okay. Okay, so you just can stick with me. Okay, now we're going to move to the status register. Okay, so this status register actually is inside of your IO register. Okay, as I mentioned previously. Okay, so the status register is at the end of your IO register. Okay, so this is your status register. Okay, so what this status register do? Okay, so like other microprocessor, the AVR has a flag register to indicate arithmetic conditions such as the carry bit. So the flag register in the AVR is called a status register. So this status register is a 8-bit register that contain of the flags, okay, from of C, Z, N, V, S, H, I, T that are called a condition flags, okay, in which this condition flag will indicate some condition that result after an instruction is executed. Okay, so the status register will tell the CPU what happened, okay, after you execute a certain instruction. Either that one is have a carry flag ataupun that one is a negative number, that one is a sign number. Is it after you execute that number, you have an overflow and all those things. Okay, so you have 8 flags here actually. Okay, you have the C stand for the carry flags. Okay, so this carry flag is set whenever there is a carry out from bit 7, in which after an 8-bit addition or subtraction. Okay, for example, I just put a simple example. Okay, you're going to add 2 numbers or 2 8-bit numbers. Okay, so this is a bit 0. This is B0 and this is B7. Okay, after you do the addition, what happens is the answer will be something like this. Okay, 1 plus 1, you get 0 and you have a carry there. So what happened? Now, you see here, from bit 7, you have a carry to bit 8. So every time you have a carry, so automatically the C will be set. Okay, the C is set, will be set 1. Okay, inside of the status register. Okay, if you add these two numbers and then the answer, there is no carry, okay, from bit 7 to bit 8, then the C will be 0. Okay, and then we look at the 0 flags. Okay, so these flags reflect the result of an arithmetic or logic operation. Okay, if the result of is 0, then Z equal to 1. If the result is not 0, then Z equal to 0. Okay, so by referring to this example here, you add these two numbers and then you see here, the result here, you have a value. Okay, you see you have a value 1. So the Z is set 0. Okay, will be cleared 0. If you add two numbers, contohlah you have this number here, 1 0 0 0 0 0 0 0 plus with 1 0 0 0 0 0 0 0. You add this number here, so you will get 0 0 0 0 0 and carry. Okay, so after you execute this instruction, okay, after you did this after you do this operation, what happened here? C will equal to 1. Why? Because you have a carry there. And meanwhile, Z equal to 1. Why is Z equal to 1? You see there, the result here, no value, which is produce 0. So that's why Z equal to 1. Okay, if the result have value, okay, then Z equal to 0. Okay, then we have the negative flags. Okay, so this flag here, binary representation of sign number use a bit 7 as the sign bit. Okay, so this bit 7 here actually used for the sign bit. Okay, So the flag reflect the result of the arithmetic operation. So every time you do the operation and then you see the bit 7 here is 0, then what happen here? The CPU know that the result is in positive numbers. If the bit 7 here is 1, so the end will be 1, which is result is negative number. Okay, so then we have the overflow flag. Okay, the V flag. Okay, the flag is set whenever the result of a signed number operation is too large, causing the high order bit to overflow in the signed bit. Okay, for example lah. Okay, you're going to add two signed number. Okay, you know that both number are a signed number. Okay, so since you know that both are signed numbers, so this one here, by right, the bit 7 here to indicate this is a signed number. So when you add this number here, what happens is, okay, you will get something like this. Okay, this is a bit 6 and this is a bit 7, yeah? Okay, so you will get 1 plus 1, you get 0, and then suddenly, okay, you have a carry from bit 6 to bit 7. So now the CPU know that there is overflow occurs, okay, because the value from this addition overflow to the signed bit. So now the B equal to 1. Okay, this is only valid for the signed number. Okay, if you're going to add signed number, right? And then the S, okay, the sign flag, okay, the flag is the result of exclusive O-ring of N and V flag. Okay, so this sign flag, okay, the sign is actually when it will be determined, okay, by exclusive or your N flags with your V flags. Okay, and last but not least, the H flags. Okay, so this H flag indicate that if there is a carry from bit 3 to bit 4 during addition or subtraction operation, then this bit is set, otherwise it is cleared. Okay, so let's say lah, okay, now this is bit 0, 1, 2, 3, and this is bit 4. Okay, you see here, when you add this number here, 0 plus 0, you get 0. Then there is no carry from bit 3 to bit 4. So what happened here? H equal to 0. Okay, let's say lah, if this one here, you got carry 1 plus 1, okay, which is equal to 1, 0. Okay, you put 0 here, and then you have a carry there. Then automatically H equal to 1. Okay, so that is for the half carry flags. Okay, and then another two flags here for T and I. Okay, T is for the bit copy storage. Okay, this is for the testing purpose, and I is for the interrupt. Okay, whenever you're going to use the interrupt, you need to set this I bit. Okay, so that you can use. Okay, so that you can use that interrupt. If not, then the interrupt will never occurs. Okay, so let's look at the example. Okay, regarding the status register. Okay, you're going to show the status register of the Z flag during the execution of the following program. Okay, so we look line by line. So what happened here? LDI R24. So what are you going to do here? LDI R24, you're going to load value 4 to your R20. So R20 will have 4. Okay, what about your Z flag? Okay, actually for the LDI, okay, flags are not affected. Okay, why the flag is not affected? Because this is a data movement. Okay, if you see the instruction set summary, for any data movement punya what we call it instruction, okay, you see this column here, the flags are not affected. Okay, the flag only affected when you do, okay, see this one here, when you do the arithmetic and logic operation, then the flag will change accordingly. Okay, if you do the data movement, okay, so this is the data movement. Okay, no flags affected. Okay, see, no flag affected for the data movement. Okay, if you use the bit test instruction, then that is the some of them going to change lah. Okay, only for data movement, no flag affected. Okay, so now we continue next. Right, so next you decrement R20. So you decrement the R20. So now R20 equal to 3. Okay, then what happened to your Z flag? Z flags equal to 0. Why 0? Because you still have value inside of your R20. And then you decrement one more time. So now your R20 becomes 2. What about the Z flag? Z flag still 0. Why? Because you are still have the value inside of R20. Decrement again, R20 become 1, Z equal to 0. Why? Because this is still have value inside the R20. And when you decrement one more time, R20 now becomes 0. Okay, so when the R20 0, then after that the Z flag will be set. Okay, so let's do another examples. Okay, show the status of the C, H, and Z flag after the addition of 38 and 2F by using this instruction here. Okay, so let's look at this instruction. Okay, you have, okay, for the first line here, okay, load I R16080X38. Okay, so R16 will have value 38. And then after that, load I R17 with 2F. So R17 will have 2F. Okay, then after that, you add R16 with R17. Then you're going to find out what are the value of your C, H, and Z flags after you execute the third instructions here. Okay, so if you going to solve this to find out to determine the flags, the status register flags. So I advise you, okay, always change this hexadecimal number to binary representation. Okay, so then after that you can find out your H flag, your C flag, and Z flag. Okay, so 3-8. Okay, by using the 8-4-2-1 method, okay, always use the 8-4-2-1 method, or you can simply press your calculator. 3-8 is 0-0-1-1, and 8 is 1-0-0-0. What about 2F is 0-0-1-0, and this is 1-1-1-1. Okay, you add them. And what happened here is 0 plus 1, you get 1. 0, 1 is 1. 0, 1 is 1. 1 plus 1, you get 1, 0. Okay, so you have a carry there. 1 plus 1, you have 1, 0. You have a carry. 1 plus 1 is 1, 0. Plus with 1, you have got 1, 1. So you have another carry. And this is 1 and 0. So the final answer will be here is 6, 7. Okay, now we're going to identify these flags here. Okay, so what are C flags? Do you have any what we call here carry flags from bit 7 to bit 8? Ada tak? Is there any carry flags beyond bit 7?
No.
No
No.
carry flag, so you put 0 there. And what about the Z flag? Okay, since you have the value inside of after you do this operation, then the Z flag is also 0. What about the H flag? Where we're going to look at the H flag. Okay, you're going to look at bit number 3 and bit number 4. Is there any carry from bit 3 to bit 4? Ada tak?
Yes.
Yes, there is carry here. So now H equal to 1. Okay, let's do another example. We have a few examples left. Okay, show the status of the C, H, and Z flag after the addition of this number here. Okay, again. Okay, R20 9C, and then you have R21 64. Okay, again, change this one to has binary representation. So you will get 1001. What about C? What is C? A, B, C. C is 12. Okay. 1100 and 64 is 0110. 4 is 0100. You add them up. Okay, so 1 plus 1 is 0. 1 plus 1 is 1 0. 1 plus 1 is 1 0. 1 0. 1 0. Okay, now we're going to determine what is H, C, and Z. Can you tell me what is H? Is there any carry from bit 3 to bit 4? Yes, there is a carry there. So H equal to 1. What about C flag? Is there any carry beyond bit 7? Ada tak? Okay, you have. Okay, so the C equal to 1. What about the Z? Okay, since the Z is 0, okay, the result is 0, then Z equal to 1. Okay, so this is another example. So I think you can do it by your own. Okay, then we finish our module 2. Okay, any question?